Okay, so hopefully you've already watched the video on alkanes, the simplest of our hydrocarbons, our saturated hydrocarbons. Single bonds only, substitution reactions, or combustion reactions. Now we're going to look at the addition reactions of alkanes. This should be some revision for you from Year 11 organic content, but we need to pay close attention to the reagents and the conditions here that you may not have done in Year 11. So let's get started. Of course, we're talking about alkenes. So alkenes will undergo combustion reactions similar to alkanes, but the chemical properties of a homologous series are caused by the carbon-carbon double bond. This means that in addition to our combustion reaction, alkenes will undergo addition reactions. So not substitution, these are addition. A small molecule is going to be added at the site of the double bond and typically to each side of the double bond. So where we would have the double bond normally, the double bond will break and we're going to add something to one side and something to the other. This means that two molecules are going to combine or add together to form a single molecule. We'll have no byproduct being formed like the HCl or things like that we saw in substitution reactions. We're going to go from two or more reagents, well, two reagents into a single product. The carbon-carbon double bond will break, making and form a new carbon-carbon single bond. Okay, so we're going to go from something that may have had trans or cis isomerism to now having free rotation around that carbon-carbon single bond. We will take an unsaturated molecule and it will become saturated because we will have single bonds only. Let's start looking at these reactions. The first ones that we're going to be looking at, we're looking at a smaller molecule added across the double bond with an atom or group from the molecule added to each of the carbon atoms in double bond. So if we have a look at this example here, we're taking ethene. We are adding hydrogen bromide. This will break. Hydrogen will add to one side and bromine will add to the other. So what we will end up with is the monosubstituted haloalkane. Okay, but there is only one product and it now has a single bond between the two carbons here, not the double bond that we started with. So unlike substitution reactions, there's no inorganic byproduct formed. During the addition reaction, all the atoms end up in the final product. So we have more of the reactant atoms ending up in the final product, so we would have higher atom economy. These can occur with a number of small molecules. So we can have hydrogen, okay, which is hydrogenation, where we add H2 across the double bond. Halogens, so again our Cl2, Br2, etc. Halogen halides, which are your HCl, HBr, and even water, our H2O. All of these have different conditions depending on the nature of the reactants that we're using, and we need to know what they are. The first of these is the hydrogenation, so we're adding H2 across the double bond, so we are simply going from an unsaturated alkene into a saturated alkane because we're adding hydrogen on either side. This requires nickel as a catalyst, so you'll often see nickel being written down below. It'll be nickel solid and then H2 gas being added across, and we go from the alkene through to the corresponding alkane. None of these reactions cause the chain to get longer. So if my reactant has two carbons in it, my product will also have two carbons in it. We are not extending the chain, we're just going from a double to a single bond. With bromine, this is something that we often use as a test for the presence of a carbon-carbon double bond, and this is because bromine is a dark orange-brown color when it is in Br2, so it'll be orange. When we cleave that bond, it loses its color, or it decolorizes. So when the bromine adds across the double bond, forming the dihalogeno, okay, because we're going to add 2 halogens, bromine on each side. So here we've got 1, 2 dibromoethane. Okay, we lose the color. This is a common thing where they will ask you to describe the color that would occur, or what would occur, or they'll ask you for a chemical test to determine between some unknown organic compounds, and one of them might be suspected to be an alkane. This is known as the bromine water test, okay, and it is the bromine test for unsaturation. So alkene plus Br2 goes to the dibromo compound, and in the process we start with this orange liquid that decolorizes. Okay, it becomes colorless. You don't want to refer to this as clear, because this is a clear orange solution, this is a clear colorless solution, and this is our organic product up here. This is our organic, our bromoalkane. Okay, at the top. And of course, because it is non-polar, it's not, they're immiscible, they're not mixing. So this is our organic, which is less dense than water. The bromine here has gone and moved into here, reacting with the alkene, decolorizing the bromine liquid, leaving our organic product on top. So let's start to look at the conditions and the products that we have. When we have hydrogen halides, these will undergo addition reactions, which we may end up with a non-symmetrical product. Okay, so if you think, if we just have something like ethene, if I add a hydrogen halide to this, such as HCl, it doesn't matter which side my hydrogen goes on or which side my chlorine goes on, because it will always be chloroethane. I'm going to it's going to be carbon number 1 from wherever this one is. But if I have, say, this one here where we've got 1, 2, 3, 4, so this is going to be but1ene. If the hydrogen adds on here and then the chlorine here, it's going to give us 2-chlorobutane. Whereas if it adds the other way and we end up with the chlorine adding onto this carbon and the hydrogen onto this one, we're going to have 1-chlorobutane. So in this case, we can get a mixture of isomers. And this is important to remember, because we have no way within the VCE course of talking about which one would be the preferred isomer or which one would turn out the most. So depending on if we are talking about butenes, pentenes, where that double bond is and how the addition occurs across the double bond can produce different isomers. Okay, when we talk about water, previously we've talked about Br2, or Cl2. These will happen at room temperature with no heating required, no catalyst required. Same goes for HCl, HBr. These are quite reactive reagents. They don't need extra help. When we're talking about water, we are now trying to break this bond here in order to add OH to one side and hydrogen to the other. This is going to require a catalyst. It is 300 degrees C and then a H3PO4 solid catalyst. This is phosphoric acid. Okay, and in that case, water will be gaseous. You will also see this written again using our above and below the arrow notation, H2O gas, and then 300 degrees C, H3PO4. And this will produce the corresponding alkanol. Again, here we have added hydrogen to one side and then we've added our OH to the other, our hydroxyl, producing our alcohol. So here we are going to have ethanol. This is known as a hydration reaction because we are adding in water. Okay, and it will produce the corresponding alkanol. Again, depending on where the position of the double bond is and the way that the water attacks across the double bond, we can end up with a mixture of isomers, either being the primary or the secondary alcohol in longer chains. So we have hydrogenation, which is the adding of hydrogen. This is going to be at warm temperatures using nickel. Okay, we have hydration, where we add water across the double bond to form the corresponding alcohol, and this requires a concentrated acid and high temperatures. The last one that we're going to talk about is addition polymerization. Okay, and this should definitely be a revision from year 11. We don't need to know as much about polymers as we did in year 11. We do need to be able to draw monomers from polymers and polymers from monomers. Remembering polymers are many, many carbons long. They can be hundreds of carbons long. We only cover at this stage addition polymerization, so all the monomer goes into the following polymer. The monomeric, I would say this is the monomeric repeat, is represented with large square brackets with an N, making sure to leave the bonds open, indicating that it extends in both directions in the polymer. And this is saying for N number of repeats. This is not what we would call a monomer if we were asked to draw the monomer, because for an addition reaction, the monomer of the polymer must contain a double bond. So to draw this as a monomer, we would put our double bond in and then just add what was on each carbon. In this case, we are just going to have ethane because this is a representation for polyethene. So with addition polymerization, we're going to say that it requires a catalyst. We don't need to know which one, and then we are often asked to draw a segment. Generally, we will be asked to draw 3 repeats, which is going to be 6 carbons. 1, 2, 3, 4, 5, 6. Keep the bonds open at each end. Square brackets around the repeating area and an N. Okay, so we would essentially draw 3 equivalents of the monomer joined together in a polymer. It doesn't matter what has been attached to it, we will simply go through this process where we remove the double bond, keep what was on each carbon on the carbons, and then close up our polymer to show our repeats here. So, in a summary, the reactions of the alkenes that we need to know, we have addition polymerization, which will require a catalyst and monomers, the hydrogenation with H2 and a nickel catalyst, dihalogenoalkanes, so adding Br2, Cl2, F2 will give us a dihalogeno, non-symmetrical monosubstituted halogenoalkane using our hydrogen halides, and then we can also form alcohols using H2O and either conc H2SO4 or H3PO4 at 300 degrees C, with water being steam. The reactions of these alkenes are important for industry. It's things, hydrogenation gives us margarine, hydration of ethene will allow us for the industrial production of ethanol, polymerization, of course, with the production of plastics, and we can also, these often are useful in the synthesis of drugs and medicines, and also antifreeze. So these reactions are incredibly important throughout industry. Again, make sure you write a summary so that you know all the reagents and the products that they form with their general equations, and then have a go at your textbook questions 1 to 5 on page 344 to consolidate this information. And I'll see you in class.